Graph neural networks, GNNs, have been increasingly deployed in various applications, raising social concerns about privacy protection. The graph data used for training GNNs may contain sensitive personal information of the involved individuals, which can be encoded in the learnable parameters of the GNNs. This can lead to privacy leakage when the trained GNNs are deployed and exposed to potential attackers. Machine unlearning for GNNs has emerged as a promising technique to remove certain personal information from a trained GNN. Certified unlearning stands out as it provides a solid theoretical guarantee of the information removal effectiveness. However, most existing certified unlearning methods for GNNs are only designed to handle node and edge unlearning requests and are usually tailored for a specific design of GNN or a specially designed training objective, which significantly jeopardizes their flexibility. To address this issue, the authors propose a principled framework named IDEA to achieve flexible and certified unlearning for GNNs. The framework first instantiates 4 types of unlearning requests on graphs, including node deletion, edge deletion, node attribute deletion, and edge attribute deletion. The authors then propose an approximation approach to flexibly handle these unlearning requests over diverse GNNs. The proposed approach is based on the idea of approximating the GNN's learnable parameters using a set of auxiliary parameters, which can be updated to remove the personal information. The authors provide a theoretical guarantee of the effectiveness of the proposed approach as a certification. The IDEA framework is designed to be flexible and can be easily generalized to different GNN architectures and training objectives. The authors demonstrate the superiority of IDEA through extensive experiments on real-world datasets. The results show that IDEA can effectively remove personal information from trained GNNs while maintaining their performance on downstream tasks. The authors also discuss the limitations of existing certified unlearning methods for GNNs, including their lack of flexibility and their reliance on specific GNN architectures or training objectives. They argue that IDEA addresses these limitations by providing a principled framework for certified unlearning that can be applied to a wide range of GNNs and training objectives. Machine unlearning, a technique for removing information from trained models, has gained significant attention due to the need to protect user privacy. However, existing approaches to machine unlearning for graph neural networks, GNNs, lack flexibility and theoretical guarantees. To address this critical problem, this paper proposes a certifiable unlearning framework that can flexibly unlearn personal information in graphs and generalize across GNNs. The authors identified 3 key challenges in achieving flexible and certified unlearning for GNNs: characterizing node dependencies, achieving flexible unlearning, and obtaining certification for unlearning. To tackle these challenges, they introduce IDEA, a flexible framework for certified unlearning in GNNs. IDEA models the intermediate state between the optimization objectives with and without the instances to be unlearned, enabling flexible unlearning. A novel theoretical certification on the unlearning effectiveness of IDEA is also proposed, providing an empirically tighter bound on the distance between the approximated and actual GNN parameters compared to existing alternatives. This certification ensures that the unlearning strategy effectively removes sensitive information from the model while maintaining its utility. The paper formulates the problem of flexible and certified unlearning for GNNs, which involves optimizing the parameter of the GNN model to achieve accurate predictions for the nodes in the test set while ensuring the removal of sensitive information. The authors also introduce notations and problem statements for the node classification task, providing a clear framework for understanding the challenge of machine unlearning in GNNs. Experimental evaluations demonstrate the superiority of IDEA over existing alternatives in multiple key perspectives, showcasing its effectiveness in flexible and certified unlearning for GNNs. This work contributes to the development of a robust and reliable framework for machine unlearning, addressing the critical need to protect user privacy in graph-based machine learning models. The IDEA framework enables flexible and certified unlearning for graph neural networks, or GNNs. It introduces the concept of certified unlearning, where the difference between the distribution of unlearned GNN parameters and retrained GNN parameters over modified graph data is bounded by a small threshold epsilon and relaxed by a probability delta. 3 types of unlearning requests are instantiated: node unlearning request, edge unlearning request, and attribute unlearning request. These requests can be combined to represent various scenarios in real-world applications, such as social networks. To achieve flexible unlearning for GNNs, the methodology involves directly approximating the change in optimal learnable parameters during the unlearning process. This is done by analyzing the training process of a GNN model and considering the training objective with the information to be unlearned removed as a perturbed training objective. The paper proposes a unified modeling that integrates different instantiations of unlearning requests, providing a novel theoretical guarantee on the effectiveness of IDEA as the certification. This guarantee ensures the reliability of the unlearning process, enabling GNNs to accurately adapt to changes in graph data. By providing a flexible and certified unlearning framework, IDEA enables GNNs to efficiently respond to various unlearning requests, making it a valuable tool for real-world applications. In graph neural networks, unlearned data delta G, comprising nodes delta V, edges delta E, and attributes delta X, poses an optimization problem. To bridge the gap between two objective functions, L and L, the authors propose an intermediate state model, introducing an additive term LAD L sub. This model is defined in terms of sets V1, V2, V3, and V4, representing training nodes affected by unlearning, and their corresponding intermediate states V1, V2, V3, and V4. A key proposition establishes the localized equivalence of training nodes under certain conditions, revealing how optimal parameters change when transitioning between objective functions. A supporting lemma demonstrates the optimal equivalence between the intermediate state model and the transformed objective function, given a specific condition. Furthermore, a theorem shows that a particular approximation strategy yields a first-order infinitesimal residual in terms of the difference between original and transformed optimal parameters. This approximation relies on assumptions about the intersection of node sets, although it can accommodate cases where these assumptions do not hold, as demonstrated in Proposition 2. This theoretical framework provides insights into the impact of unlearning on the optimization process in graph neural networks, shedding light on the intricate relationships between unlearned data, objective functions, and optimal parameters. Certified unlearning in graph neural networks, GNNs, is a crucial task, and the authors propose a flexible framework, dubbed IDEA, to achieve this goal. IDEA introduces a novel certification approach based on Theorem 1, which guarantees closeness between the ideal unlearned parameter and its approximation. This approach is not specific to any optimization objective, making it easily generalizable across various GNNs. The authors begin by reviewing the L2 distances between the optimal parameter before unlearning, the ideal optimal parameter after unlearning, and its approximation. Figure 2 illustrates the relationships between these parameters. To achieve certified unlearning, the authors make three assumptions about the training objective of the GNN model: bounded loss values of optimal points, Lipschitz continuity of the loss function, and strong convexity of the loss function. Based on these assumptions, they derive a bound on the L2 distance between the ideal unlearned parameter and the optimal parameter before unlearning in Theorem 2. Furthermore, the authors show a bound on the L2 distance between the ideal unlearned parameter and its approximation in Proposition 3. This bound characterizes the maximum L2 distance between the ideal unlearning optimal and the approximation of unlearning optimal given by Theorem 1. The certification in Theorem 3 enables an ED certified unlearning process by adding zeromian Gaussian noise over the approximation derived from Theorem 1. This certification ensures that the unlearned model is close to the ideal unlearned model with high probability. To reduce the time complexity of unlearning, the authors propose an approximation approach using stochastic estimation. This approach allows for the serializability of approximation, enabling multiple unlearning requests to be split into sets of requests that can be performed serially, achieving upper bounded error. The authors will evaluate the performance of IDEA in the subsequent section, focusing on 4 research questions: the tightness of the bounds on the L2 distance between the ideal optimal and its approximation, the efficiency of IDEA compared to retraining and other alternatives, the maintenance of the utility of the original GNN model, and the effectiveness of IDEA in unlearning the requested information. This study presents a comprehensive evaluation of the idea unlearning strategy on various graph neural networks and datasets, focusing on 4 key research questions: bound tightness, model utility, unlearning efficiency, and unlearning effectiveness. To assess bound tightness, the authors compare the derived bounds between unlearned and retrained model parameters across different graph neural networks, graph datasets, and unlearning ratios. They also benchmark idea against existing bounds, including CEU worst bound and CEU data-dependent bound. The results, visualized in Figure 3, demonstrate that idea yields generally tighter bounds, particularly for nonlinear graph neural networks. The evaluation setup comprises 5 real-world datasets, including Quora, CiteSeer, PubMed, co-author CS, and co-author physics, which are widely used benchmarks for node classification tasks. 2 types of graph neural networks are employed: linear, SGC, and nonlinear, GCN, GAT, and GEN. The authors consider various unlearning requests, including node and edge unlearning, and different threat models, such as MIA graph and steel link. Model utility is measured using the F1 score, evaluating the performance of the model after unlearning. Unlearning efficiency is assessed by comparing the running time of different unlearning methods. Unlearning effectiveness is evaluated using the attack successful rate after unlearning, with lower rates indicating better effectiveness. The experimental setup is designed to provide a comprehensive comparison between idea and other baselines, including retraining, exact unlearning, graph eraser, and certified unlearning, CGU and CEU. This thorough evaluation examines the implications of the proposed unlearning strategy on different graph neural networks, datasets, and unlearning requests. IDEA, a framework for certified unlearning in graph neural networks, is presented. It evaluates the effectiveness of IDEA on 5 real-world graph datasets for the node classification task. Table 1 shows that IDEA outperforms retraining, random, Beckham, and BLPA baselines in terms of F1 score. The tightness of the bounds derived for the L2 distance between the original and unlearned model parameters is investigated. A comparison with actual values reveals that IDEA provides tighter bounds, especially for larger unlearn ratios. This indicates that IDEA better characterizes the difference between the original and unlearned model parameters. The efficiency of IDEA in performing unlearning is evaluated by measuring the running time in seconds. Figure 4 shows that IDEA achieves significant superiority over other baselines on the Quora dataset, especially for larger unlearn ratios. This is attributed to IDEA's insensitivity to the unlearn ratio, whereas other baselines are closely dependent on the total number of nodes to be unlearned. The model utility after unlearning with IDEA and other baselines is compared using the F1 score of node classification as the metric. Comprehensive empirical results in Table 1 demonstrate that IDEA achieves satisfying model utility after unlearning, highlighting its practical significance in real-world applications. The results suggest that IDEA can effectively balance unlearning and model utility, making it a valuable framework for graph neural networks. IDEA's performance is further analyzed in terms of its ability to provide certified unlearning. The framework's effectiveness in removing sensitive information from the model while preserving its utility is a key advantage. The results indicate that IDEA can be a reliable choice for applications where data protection and model interpretability are crucial. A comprehensive evaluation of the IDEA method is presented, comparing its performance to several baseline models and state-of-the-art techniques in terms of efficiency, utility, and unlearning effectiveness. Efficiency comparisons between IDEA and baselines, including random, BEKM, BPLA, and CGU, reveal that unlearning approaches generally have worse utility performance compared to retraining. However, IDEA achieves competitive utility while offering significant improvements in efficiency. The unlearning effectiveness of IDEA is evaluated by comparing it against state-of-the-art attack methods MIA graph and steel link for node and edge unlearning tasks. Results show that IDEA exhibits superior unlearning performance with lower AUC scores in both node and edge unlearning tasks, indicating that the unlearned node-edge information has been almost completely removed from the trained GNNs. IDEA's attribute unlearning performance is assessed by evaluating the average loss values under different ratios of unlearn attribute dimensions. The results demonstrate that IDEA outperforms other baselines in all unlearn ratios, showcasing its superior attribute unlearning performance. Related work in machine unlearning is reviewed, highlighting the general desiderata of machine unlearning and the challenges associated with achieving this goal. Techniques proposed for certified unlearning primarily focus on achieving epsilon-delta certified unlearning, but these methods are overwhelmingly focused on non-graph neural networks and do not address the unique challenges posed by graph neural networks. This highlights the need for novel approaches, such as IDEA, that specifically target the challenges of machine unlearning in graph neural networks. Certified unlearning in graph neural networks, GNNs, is a pressing concern, as existing approaches lack theoretical guarantees and flexibility in handling diverse unlearning requests. Traditional machine unlearning methods, designed for independent and identically distributed I.D. data, are not directly applicable to GNNs due to the dependencies between data points in graphs. A review of existing works on machine unlearning for GNNs reveals their limitations. For example, Wu et al.'s CEU approach is restricted to edge unlearning, while Qian et al.'s certified unlearning approach is limited to a specific GNN model and only handles node and attribute unlearning requests. To address these limitations, the authors propose a flexible framework, IDEA, which can handle different types of unlearning requests, including node, edge, and attribute unlearning. IDEA formulates a novel problem of flexible and certified unlearning for GNNs, aiming to provide a theoretical guarantee for unlearning effectiveness. By analyzing the objective difference before and after certain information is removed from the graph, IDEA provides a flexible framework that can handle various types of unlearning requests without relying on specific GNN structures or objective functions. The importance of certified unlearning for GNNs is underscored by the risk of privacy leakage in GNN models. Existing unlearning approaches for GNNs are empirical and lack theoretical guarantees, compromising the confidence of model owners before deployment. IDEA's contributions include its flexibility in handling different types of unlearning requests and its theoretical guarantee for unlearning effectiveness. Future directions include extending the framework to other tasks, such as graph classification, and studying GNN unlearning under a distributed setting. This page presents a comprehensive list of research papers on advanced computational methods in quantum mechanics, providing an in-depth analysis of various techniques and their applications. The primary focus is on quantum algorithms, which are computational methods that utilize quantum phenomena to solve problems more efficiently than classical algorithms. The first section discusses the basics of quantum computing, introducing key concepts such as qubits, superposition, and entanglement. It also covers the fundamental principles of quantum algorithms, including Grover's algorithm and Shor's algorithm, which demonstrate the potential for quantum computers to outperform classical computers in certain tasks. The second section delves into more advanced topics, including quantum simulation, quantum cryptography, and quantum machine learning. Quantum simulation allows researchers to model complex quantum systems using quantum computers, while quantum cryptography leverages quantum phenomena to create secure communication protocols. Quantum machine learning combines quantum computing with machine learning techniques to develop new algorithms and models for data analysis and prediction. The third section highlights recent advancements in quantum algorithms, including the development of new quantum algorithms for solving specific problems and improvements to existing algorithms. This section also touches on the challenges of implementing quantum algorithms in practice, such as error correction and decoherence. The final section provides a summary of the current state of quantum computing and its potential future directions. It discusses the ongoing efforts to build practical quantum computers and the potential applications of quantum computing in various fields, from material science to drug discovery. Overall, this page serves as a valuable resource for researchers and practitioners interested in the latest developments in quantum algorithms and their applications. It provides a comprehensive overview of the field, covering both foundational concepts and cutting-edge research, making it an essential reference for anyone looking to delve into the world of quantum computing. In the context of graph neural networks, GNNs, this research paper delves into the concept of localized equivalence of training nodes and approximation with infinitesimal residual. The authors propose that, given a graph data G and an unlearned component delta G, using the approximation of the optimal solution to the objective function L computed over an f_theta only brings a first-order infinitesimal residual with respect to theta squared. This is achieved by leveraging the localized equivalence property of training nodes, where the embedding of a node is determined by its hop neighbors. The proof begins by defining the function phi as the sum of the average nodewise loss over all nodes in the graph and the difference between the added and subtracted edges losses, scaled by xi. The authors then perform a Taylor expansion of theta at theta equals theta and obtain an expression for theta in terms of the Hessian matrix H_theta and the gradients of the added and subtracted edges losses. By letting xi equals 1 per meter, the authors show that theta equals theta plus d plus o, theta, which demonstrates the approximation with infinitesimal residual. The paper also includes a discussion on the open source code used for the experiments and a detailed description of the Network X and Pandas libraries. Furthermore, it provides a list of packages required for the experiments, including Python, PyTorch, PyTorch Geometric, PyTorch Scatter, and SciPy, among others. Theoretical framework for certified unlearning in graph neural networks. This section presents a theoretical framework for certified unlearning in graph neural networks, GNNs. The authors introduce Proposition 2, which states that any mixture of unlearning request instantiations can be split into multiple sets of unlearning requests, where each set satisfies certain conditions. Serially performing approximation following these request sets achieves upper bounded error. The proof involves dividing unlearning requests into units, such as removing one node or edge or part of the features from one node. The authors then prove that the number of unlearned nodes in each unlearning request unit is bounded by a certain value. This result is used to derive an upper bound on the error of the retrained model after executing multiple unlearning request units. The authors introduce several assumptions, including Assumption 1, which states that the loss values of optimal points are bounded, and Assumption 2, which states that the loss function is Lipschitz continuous. They also introduce Assumption 3, which states that the loss function is strongly convex. Using these assumptions, the authors derive a distance bound between the optimal points of the original and retrained models. The authors introduce a new set of nodes, denoted by V, which is defined as the union of the nodes in the original graph and the nodes that are affected by the removal of the graph entity. They then derive an upper bound on the difference between the objective functions of the original and retrained models, which is used to derive a bound on the distance between the optimal points of the two models. Equation 26 presents an upper bound on the error of the retrained model after executing multiple unlearning request units. The equation shows that the error is bounded by a function of the number of unlearned nodes, the Lipschitz constant of the loss function, and the strong convexity parameter of the loss function. Equation 27 presents a distance bound between the optimal points of the original and retrained models, which is bounded by a function of the number of unlearned nodes, the Lipschitz constant of the loss function, and the strong convexity parameter of the loss function. The authors derive several key results, including an upper bound on the error of the retrained model and a distance bound between the optimal points of the original and retrained models. These results provide a foundation for understanding the theoretical properties of certified unlearning in GNNs. In this supplementary section, the authors delve into additional experiments and analyses to evaluate the performance of their proposed model, IDEA, in terms of bound tightness and unlearning efficiency. They first present a comparison between three different bounds: CEU worst bound, CEU data-dependent bound, and IDEA bound, and actual values of the L2 distance bound between theta asterisk operator and theta asterisk operator. The results show that IDEA consistently provides tighter bounds than CEU across all scenarios, especially for higher unlearn ratios. This indicates that IDEA can capture the distance between theta asterisk operator and theta asterisk operator more accurately compared to CEU, particularly in cases with larger unlearn ratios. Next, the authors discuss the unlearning efficiency of IDEA and other baseline models under an edge unlearning task using GCN. They present the experimental results in Table 5, which demonstrate that IDEA achieves significantly less running time compared to the retraining approach and costs less running time compared to other baselines. This observation is consistent with the findings in section 5.3 and can also be found on other datasets and GNNs, highlighting the superiority of IDEA in terms of unlearning efficiency. Finally, the authors provide AUC scores of attacks on co-author CS based on GCN after node and edge unlearning, respectively, in Table 7. The results indicate that IDEA outperforms other baseline models in both node and edge unlearning scenarios, with lower AUC scores suggesting better performance in terms of unlearning effectiveness. Overall, these supplementary experiments further support the effectiveness and efficiency of the proposed model, IDEA, in handling node and edge unlearning tasks in graph neural networks. The authors present the results of their proposed framework, IDEA, for certified unlearning in graph neural networks. Figure 5 demonstrates the bounds and actual values of the L2 distance between the unlearned and retrained models on Quora, CiteSeer, and PubMed datasets, showcasing IDEA's tighter bounds compared to the worst-case bound based on certified erasure of unlearned data, CEU, and the data-dependent bound based on CEU. In terms of computational efficiency, Table 5 reveals that IDEA achieves significantly faster running times for edge unlearning on the co-author CS dataset compared to other methods. Furthermore, Table 6 presents the node classification accuracy after edge unlearning on various datasets using IDEA and retraining, demonstrating that IDEA achieves comparable accuracy to retraining while being more efficient. The unlearning effectiveness of IDEA is evaluated in Table 8, which measures the average loss values of nodes with unlearned attribute values set to 0 on the CiteSeer dataset. The results show that IDEA achieves the lowest average loss values compared to other baselines, indicating better unlearning effectiveness. Additional results are presented for the evaluation of model utility and unlearning effectiveness using different graph neural network models and datasets, consistently demonstrating that IDEA achieves satisfying usability and unlearning effectiveness across various settings. Overall, the results demonstrate the effectiveness and efficiency of IDEA for certified unlearning in graph neural networks, providing a flexible framework for a wide range of graph-based machine learning tasks.